So welcome to talk on dealing with JVM limitations in Apache Cassandra. We're not going to talk really about using Cassandra or anything like that today, but just out of curiosity, has anyone used it? Wow. Oh, wow. I'm impressed. Who's used it in production? Wow, that's still not bad. All right. Wow, congratulations and thank you. So I'm going to talk more about the low-level stuff we do in Cassandra to get good performance and a good user experience on top of the JVM. Some of this is more challenging than others. So if I were to summarize, the pain points of building on top of the JVM in a single word or two words, it would be garbage collection. Especially with regards to pause time, that affects latency, obviously. So in a database where we want to return response in milliseconds, if not less, obviously garbage collection is a pain. But if I were to be permitted two bullet points, then I would extend that to dealing with platform-specific code. The JVM, of course, Java's got this history of being write once, run anywhere. And that kind of fights the kind of optimization you want to do because Windows and Linux and Solaris are all kind of different animals when you get down under the hood. So some of the optimizations that we want to do are going to be a little bit platform specific. So the JVM kind of actively fights us doing this, and I'll talk about how we work around that in some ways. So in terms of garbage collection, the state-of-the-art as far as Cassandra is concerned is still doing concurrent mark sweep. We tried the G1 collector. Reports are that more recent versions of G1 have been making progress, but it's still, Cassandra just allocates too fast for it. And so what happens is it can't keep up and it falls back to a stop-the-world kind of collection anyway, even worse than CMS did in our experiences. So we have a pretty good handle on what to do with CMS to avoid stop the worlds and primarily with avoiding fragmentation. So we pretty much recommend sticking with that in the Cassandra world. The one alternative that people have been successful with, to my knowledge, is Azul's Zing JVM running the C4 garbage collector. Kind of pricey, but it works as advertised. Unfortunately, that's not a realistic option for the vast majority of use cases where we have hundreds of nodes that people want to standardize on the Oracle JDK because that's what they've certified their application on and so forth. So just really briefly, the main challenge here when talking about garbage collection with low pause time is the compaction phase. So what that means is when I've allocated space off of the heap and then that space is no longer used, so it gets reclaimed, I've kind of got a hole where that object used to be allocated. And so what I need to do is, if I have 10 megabytes of free space spread across a lot of these little holes, and then Cassandra comes up and says, hey, I'd like to allocate a 10 megabyte array, it can't fulfill that request until it combines those holes. So that combination is called compacting, and it's painful because the garbage collector has to relocate other objects in memory to do that compaction process. So in the CMS world, the young generation is always compacted, and that's actually always a stop-the-world collection. Not everyone's aware that new generation collections are also stop-the-world, but they're quick enough that we can usually get by with not caring that young generation is stop-the-world. So when people talk about stop-the-world garbage collection, they're typically talking about when the JVM has to go through the entire old generation and compact that. That's typically what we're talking about there. So what we've done in Cassandra is we've gone through our storage engine and tried to address the main places where we allocate large contiguous amounts of memory. If we allocate smaller amounts of memory, the JVM's free list mechanism does a pretty good job of keeping track of where it can allocate objects of a given size without having to do that full compacting mechanism, and life is good. So the three main places where we've gone through and done this, where we've broken up our large allocations, are these three places. And I'll explain what these mean in terms of the Cassandra storage engine in just a second. So those three are the Bloom filter, bitsets, the compression offsets, where we track what blocks of a compressed storage file correspond to which uncompressed offsets, and then large column values, because Cassandra actually technically allows you to store up to a 2 gigabyte value in a single column. Not necessarily the best idea. We typically recommend that you keep it to single-digit megabytes, but technically we will allow you to do that if you really want to. So, obviously when people are throwing workloads at us where they have column values of wildly different sizes, that can be a source of fragmentation as well, sort of user-generated fragmentation. So I'm going to dig in a little bit into how the storage engine works and how this ties into the fragmentation I'm talking about here. Cassandra uses what's called a log-structured storage engine, meaning that when you tell us to update a row, we don't go and change that row in place. Instead, we keep those updates, we append those updates to a commit log, and then we batch them up in memory in a structure called a memtable that then gets written out sequentially to disk. And then new values of rows in those new files on disk will sort of shadow older values, so that when we go at read time, we only get the newest values. But we're doing that without ever having to do random I/O on writes. So it turns out that this is actually a really good fit both for spinning disks, because we've cut out all the random I/O on writes, and then it's also a good fit for solid state disks because we're getting rid of write amplification. So this is really good for your disk lifetime. And so this is actually the main source where there's kind of a sentiment about the storage industry that I can't necessarily trust solid state disks with my data because they fail faster than spinning disks. The main reason that people have that experience is because these solid state disks are rated for a certain number of write cycles, and write amplification makes you go through them faster. So there's an entire presentation that a guy named Rick Branson gave on this subject. I won't go into that anymore today, but you can Google that if you're curious about the gory details. So to illustrate what I've been talking about, when I have a write here, so in the upper left, some client is giving me, he's updating a column in one of the rows in my storage engine. So what I'm going to do is first I'm going to append that tuple, or that column name and value tuple, to the commit log, and then I'm also going to put that into this in-memory structure called a memtable. So if you look at these slides that I'm going to go through, there's this dotted line going down the middle, and above the dotted line, that's happening in memory. Below the dotted line means I'm doing disk I/O, I'm writing something to disk. So you can see from this that Cassandra is a sparse storage engine. So you don't, if you have a null column or the equivalent of a null column in Cassandra, that's just, you don't write that column. You don't have to actually include a value for that. You just leave it out, because under the hood, we're actually storing a tuple of the column name that you're writing as well as the value. So we can add some, here in this slide, we're illustrating that a new write comes in. That's for another column in the same row. So the user's updated a second column in the same row. So you see in memory, that's been put together in the same structure. We recognize that it's part of the same row in memory. But on disk, since we're strictly doing appends to this commit log, it's a separate entry. It's not part of that same row structure. So then we add some more data to a different row, maybe do another update to a column in the first row, and then our mem table gets full. So what happens when the mem table gets full is we write that out to disk. We actually write it out in sorted order by row key for reasons that I'll explain in a bit. And then we just stream that out to disk sequentially. So one of the other things that this lets us do, which is called flushing in Cassandra terminology, is when we flush, we can go to the commit log and say, all of those modifications that we just did, they're now secure on disk, they're durable on disk, so you don't have to worry about replaying them if there's a failure and you get restarted. So what we'll do is we'll update basically the high water mark in the commit log that says this is where you need to start replaying. And if that entire commit log segment doesn't need to be replayed anymore, we can recycle it and start. We basically put it in a queue to use later. So that's basically an optimization. You can actually just throw away the commit log file and start a new one. Turns out it's more efficient to save it and recycle it later. So then if we go through this process again, we have a bunch more updates. The mem table fills up again. We flush it out to disk again. We have a new data file. So these data files are called SSTables for basically historical reasons. So you can see that since we're never doing update in place, when I've made new updates to those same rows, I didn't overwrite the data in the original SS table. I wrote out a new one. So you can see that these SS tables are going to multiply a little bit as updates come in. And we'll talk about how Cassandra deals with that later. But for now, I just want to go into a little bit about what makes the SS table tick, because this is going to explain what I talked about in terms of the fragmentation. So what we have, there's two main structures in the SS table. There's basically an index that tells us where to find data that's actually stored in it, and then there's the row and column data. So what the index is composed of is basically keys and as well as samples of the columns corresponding to that key. And you can think of them more as partitions and rows in the partition, because that's actually what it corresponds to from the user's perspective. But internally to Cassandra, we're storing them as just rows and columns. And so what happens if the user says, I want to read column C5 from row K5, I'm going to go first to the index. I'm going to look up where that row, where that data is in the data file, and then I can seek to that in the data file directly. So what we do to do this is, this index file, we keep a sampling of every 128th entry in that index file. We keep that in memory. So originally, this was just a big array of longs, basically. So since data files can get large, you can have hundreds of millions of rows in these data files. We're allocating 20, 50 megabytes at a time for these index samples. So that's a source of pain on startup, because we're actually reading those samples in on startup. But more importantly, it's a source of ongoing fragmentation as we write out new data files as data comes in. So that's where that's coming from. Not pictured here is the Bloom filter. Where that comes in is the Bloom filter is a probabilistic set of row keys. And so what we do with that is that lets us tell us, because remember, we have multiple SS tables for a given user level table that he's defined with create table users, for instance. So what I want to do is when he says select star from users where username equals Jonathan, I want to be able to go and only look at the data files that actually have data for Jonathan. I don't want to have to go look in data files that, you know, Jonathan was never updated in. So the Bloom filter lets me rule out a whole bunch of data files without ever even having to look in the index. I just ask the Bloom filter, do you have this row key? And the Bloom filter will either reply no, or it will reply probably. And so that's where the probabilisticness comes in. And if it replies probably, then we go through the index lookup. So that's those two. And then the last one that I talked about was compression offsets. So the previous slide oversimplified just a little bit, because when we write out those data files, we also compress it. And this is really easy to do for us, relatively speaking, because we never have to go and modify those rows once they're in the data file. So you know, that makes transparent compression much easier than in a B-tree-based storage engine. So what we have is the compression looks like this, where I basically have a big array of compression offsets that says, you know, I have these blocks of compressed data, typically 64 kilobytes, and so I'm going to tell it for every 64 kilobytes of compressed data, here's what offset that corresponds to in the uncompressed data file, because that's what we're going to use when we try to read, when we go and read the rows and columns. The index file is going to give us uncompressed offsets in the data file, so we have to translate that into what blocks do I now need to uncompress to give you your data. So, you know, this compression info is, you know, it's another big array that we were allocating, so we needed to break that up into smaller arrays. Now, there's been some research done into dealing with large arrays automatically, primarily by IBM. And there's actually, they have a real-time JVM that does this automatically. Unfortunately, the real-time JVM, last time I checked, doesn't support, you know, it's good for Java heaps up to about 256 megabytes or so. So not really, it doesn't support heaps large enough for Cassandra, where we're targeting 4 to 8 gigabytes typically. But it's, you know, I'd really like to see this kind of you know, automatic breaking up of large arrays get into some more mainstream JVMs. So I talked about manually breaking up these arrays into, you know, kind of subarrays in our compression offsets and in OpenBitSet. Incidentally, we started off using the JDK's bitset. That only lets you address an offset up to you know, 2 to the 31st. It's an because it's an integer offset that the methods take. So OpenBitSet is an implementation that the Lucene guys did because they needed to do you know, larger bit sets and have 64-bit addressing. So their methods take a long. So we took that. And then we basically forked it to break up the arrays into subarrays like I've been talking about. So just an FYI, if you ever need a bit set that's larger than 2 gigabytes, then OpenBitSet has your back. So the other thing that we've done, I mentioned that users can provide very large column values, and that can fragment the heap as well. So what we did there is we took a different approach, and what we did is we manually allocate 1 megabyte large slabs that we take the memtable space out of. And what we do is when the user gives us a column value that he wants to store, we put that into kind of a slice of that slab. So under the hood, we're using the byte buffer API, and we're saying, you know, I want to reserve a piece of that slab, and I'm going to copy the data into it. so that if he gives me a 64 kilobyte column value, I copy it into the slab before it gets tenured. So then cleaning up that 64 kilobyte value that he gave me, that's just young generation garbage collection, and it never fragments the heap. This is actually a source of some current work that we're doing in Cassandra for 1.2, because it turns out that we have what's called a slab allocator class, and what that does is whenever the old slab is exhausted, the threads that are looking to allocate will race as they allocate a new slab, and then they're all happy again. So what we're doing is we're making it so the slab allocator will actually allocate one more slab than it needs currently, so that it stays ahead of the allocation under very heavy update loads. So this is something that you may have heard, kind of an urban legend among mostly C developers. Sometimes you'll hear this from Python developers as well. The bad news is there's a little truth to that. And the truth to it is, when you're using things like byte buffer or concurrent skip list map, there's a lot of overhead in terms of tracking all of those the internals of those objects before you get to the thing that you're actually trying to store. So if you're running a database where people are primarily storing 4-byte integers or 8-byte doubles or whatever, the overhead of those storage structures can be significant. And what we found was in the extreme case, we get up to about 85% of the memory we were using was actually for this overhead and not for the actual data that we were storing. So one of the tools that we use for that, I wrote a library called Java Agent for memory measurements, and what that does is it's just a wrapper around the Java instrumentation library. The trick is that you actually have to run this code as a Java agent when you start the JVM to give it permission to dig under the hood. And what this does is it lets me ask java.lang.instrumentation, given this object, what's the total size of the heap that it's taking up, including all of the internal overhead. So that lets us get a handle on how much, what that overhead actually is. And the reason that we want to do that is early on, in kind of the dark ages of Cassandra, we'd make you tell us how often to flush the memtables. And you would need to turn that in terms of either number of operations on the memtable or number of bytes that you had actually inserted in terms of your user level bytes, not including all the overhead. So the number of bytes that you were giving me, if that's only 15% of the total space, that's wildly inaccurate. And so this was a big pain point for our users, because if you got this wrong, well, if you made it too small, Cassandra would not be performant because it's flushing constantly. If you made it too large, then you would run out of memory. And you would often run out of memory very painfully in a process we affectionately named GC storming, because the garbage collector will be able to collect just enough to continue for a little bit longer, at which case it will do another full garbage collection, and it will take minutes, many minutes, before it actually realizes, sorry, I'm screwed, and falls over and raises an out-of-memory exception. So what we did with this Java agent for memory measurements and java.lang.instrumentation is we were able to now have the user tell us, use 2 gigabytes of my heap for memtables, and we can now actually go in and say, hey, memtable, how large are you really? And be able to flush at appropriate times before we get too close to the danger zone automatically. So that improved the experience a lot for sysadmins running Cassandra. So one of the other things that came out of this realization that sort of these, we're using so much overhead for the containers for the data, is that we do a thing called the row cache in Cassandra, where to save having to merge different versions of your row from different places on disk, we'll preserve the pre-merged version of that, and it's a write-through cache, so whenever you update that row, we'll update the cache version as well. And so if you ever ask for data in that row, we don't actually have to go through this whole SSTable lookup. We just pull it from the cache and give it to you. So we get 50, 90 microseconds when we're reading from the row cache. So it's very, very fast. But we're wasting a ton of memory because of that whole overhead. So what we did was we decided to move the row cache out of the heap. And so the way we do that is we actually serialize the rows into basically mallocked chunks of memory. And so we wrote this class called freeable memory that uses reference counting to track this native memory that we've allocated, and then clean it up if that row gets aged out of the cache and not useful anymore. So one of the things that we thought about was, so this works really well for the row cache. We pay a small price in CPU because to actually give it back to the user, we have to deserialize it temporarily. But we're saving a ton of memory. Works very well. Could we do this with the slab allocation that we're doing with memtables? It turns out that it's painful because the reference counting that we do on the cache path is relatively limited, and there would be a lot more places we need to track it if we were actually doing it for the main memtable path. So that idea is on the back burner and likely to stay there, unfortunately. So I mentioned that we can generally overlook the fact that the young generation is stop the world, but there's been a tension that's getting increasingly apparent recently as core counts improve. So you've gone from a relatively cost-effective server being 8 cores to being 16 cores to being 24 and 32 cores. And that's not even talking about what you get when you really want to throw money at it. So the tension is that you want your young generation to be large enough that it can handle the allocation that all your cores are throwing at it without having to tenure that data because your young generation filled up before you finished the request that allocation came from. But at the same time, if you increase your young generation to not tenure that data that your increasing number of cores is throwing at it, then the Parnu collection is going to take longer and have a longer pause time. So there's a tension there. Don't have a really good answer for this, except that we probably need to tune Cassandra's defaults to use a smaller amount of young generation per core. Right now it'll do 100 megabytes per core up to a quarter of your heap. That's too much. We're probably going to cap it at 512K or a gigabyte of young generation space. So one of the other things that we've struggled a little bit with the storage engine is that copies kill performance. And it can be very difficult in Java to avoid copying regions of memory. It's especially when you're doing I/O. So what we did about almost 2 years ago, actually, was we said, okay, we can avoid copies on the write path if we use mmap. So what we're going to do is we're going to map those SS tables that we've got into memory, and then we'll just ask Java to give us a byte buffer back, wrapping a native area of memory containing the data that we're asking for. So we said, okay, we're just going to use channel.map, and we'll just map the data file, right? Not so fast. The file channel API will only give, or rather the byte buffer API that channel is backed by, only lets you access, again, 32-bit offsets. So what we have very frequently data files that are larger than 2 gigabytes. So we said, okay, we can deal with this. We can map by partitions, so we're going to take each of those partitions, we'll map them separately, and that's a pretty good workaround. Well, it turns out we also support partitions that are larger than 2 gigabytes. So there's not a whole lot we can do about that. We don't want to split a single partition across multiple mapped byte buffers, because then we have to check for every byte that we're reading, have I crossed that byte buffer boundary? Have I crossed that byte buffer boundary yet? And that's actually more expensive than it's worth. So we say that as long as most of your partitions are under 2 gigabytes, you'll be okay. For the occasional one that isn't, we'll fall back to buffered I/O, which is actually a code path we keep around for 32-bit JVMs as well. So it works out pretty well. In JDK9, they're supposedly moving to 64-bit array addressing, and hopefully this will be fixed, and we'll be able to clean this up a little bit. So far, we've run into a little bit of, we've had to do a little bit of workarounding here, but not too bad. Here's where it gets messy. What happens when I want to clean up one of those data files? So I said at the beginning or earlier that we're never doing override in place, so we need to be able to combine and clean up some of those old rows that we have sitting around taking up space on disk. So we call that compaction, which is confusing because we've been talking about garbage collection compaction. Now we're talking about Cassandra SSTable compaction. And I apologize on behalf of the big table engineers who used the same word for that process. So we've got multiple SS tables. What we want to do is we want to take those SS tables and throw away the data that's obsolete and only keep the data that's still relevant. And so that's what we're doing. We're taking multiple SS tables, combining them into one. So all these SS tables on the left that we've compacted, that we don't need anymore, we need to unmap those so we can throw them away. And so it turns out that some operating systems, by which I mean Windows, won't let you delete a data file if it's still mapped. So the problem is that the JDK does not expose any API to let you unmap something. You can map it, but then you have to wait patiently for the garbage collector to decide that it's not referenced anymore, at which point it will unmap it should it be in the mood to do so. So what we did in older versions of Cassandra was we would track this with a phantom reference. And so when the garbage collector did unmap something, we would get that notification via the phantom reference, and we'd be able to go in and delete the file. The problem was that users hated this, because what would happen is they'd go through deleting stuff out of their database, and their disk space would not go down. So this is not intuitive behavior to users of a database. So it was kind of comical, because the workaround was, well, don't worry about it, because if Cassandra notices that you're low on disk space, it will force a stop the world garbage collection for you to clean that up. And of course, that's what everyone wants to hear, right? So we switched tracks, and we decided that if the JDK wasn't going to let us do what we needed to do, we were going to go behind its back. So what we do is, the way that the JDK actually does the unmapping, once the garbage collector says it's safe to do so, is through a method called cleaner. And so we actually use reflection to go in and grab hold of that method, and when we unmap something, we go ahead and invoke that method on it manually. And no, it's totally not portable. I have no doubt it fails to work entirely on Joe's JVM or whatever. But that's what we got to do. The old playing by the rules way was not acceptable. Now, ironically, what this means is, since we're violently unmapping things out from under the JDK, we have to be very careful not to reference memory that used to be mapped and now is not, because if you do that, you will segfault the JVM, and bad things happen at that point. What we did was we basically had two options. We can reference count again everything that comes out of an SSTable that's mem-mapped, which we looked at that and said, we're never going to get all the bugs out if we try to do that. Or we can just go ahead and copy it out of the direct buffer when we read it, and then we don't have to worry about it getting unmapped later. And that's what we ended up doing. So we've lost a little performance by doing this because we are now again back to copying things out. It's better than it was back when we were doing buffered I/O, because when you're doing buffered I/O, first you read it into a buffer and then you copy it again into your data structure. So we've skipped the copy it into the buffer. We're relying on the operating system page cache to do that for us via mmap. So we're still a little better than we were back in 06. But not quite as fast as we were in 08 on this particular code path. We've made up for it in other respects, so our benchmark results are still better, but we did lose some performance here. But it was worth it on balance to get the behavior that users expect, that when you delete stuff, disk space goes down. That's what people need to see. So that's kind of the introduction to stuff we do that the JDK doesn't really want us to do. Another thing that we do is do a lot of hard linking. So that's where we basically tell the file system, I want to have two references to the same piece of data. So we do this for snapshotting, which works really well since we, again, we're never doing update in place. Once we have that data file written out, it doesn't change. So if you tell me I want you to snapshot your data, as of this point in time, what I'll do is I will flush whatever data I have in the memtables right now, and then I'll just go ahead and create hard links to whatever set of data files I have. And it's a little more complicated than that because we need to be consistent while compaction's going through and churning things up, but that's the basic idea. So the only way to create a hard link up until Java 7 was to use like runtime.exec. Now forking every time you want to create a link, when you want to create dozens of links, that's actually, even with copy on write forking, that can cause pain, especially when people have told their operating system not to overcommit memory, at which point trying to do runtime exec to do a snapshot will actually cause it to swap because you've forked that entire 8 gigabyte heap or whatever, and so even though you're not actually going to do anything with it, the operating system will say, uh-oh, that's a huge allocation and that may need to be backed by actual RAM, so I'm going to start swapping. So also not a great experience. So what we did was, and what we still do, is we use a library called Java Native Access, JNA, to invoke C functions from the operating system. So another one of those C functions that we want to call is mlock all. So this also relates to swapping. This is a little bit Linux specific, but there's a kernel parameter called swappiness that you can tune in Linux. And it's commonly believed that setting swappiness to 0 means you will not swap. This is not true. And as evidence, I give you the line from vmscan.c that's responsible for determining whether Linux should swap something. It's basically saying you can see that there's 3 components there besides swappiness. So swappiness can be 0, and it can still decide that I'd better swap something. So what happens in the Java world, and in particular in an application that mmaps a lot of data like Cassandra, is Linux will go and say, wow, you've really been reading these mmap files a lot. Those are super important, so I won't swap those. But all this 6 gigabytes of your heap or so, you haven't touched that in a while. I'm going to swap that. And so then when Java gets around to actually going and needing to run a garbage collection against that data, everything goes to hell very quickly. So what we do is when we start up, we call mlock all and we give it the current argument, which says just lock what I've allocated right now. Don't try to lock everything I allocate later. Which is to say we don't want it to try to allocate. We don't want it to try to lock our row cache. Or most importantly, we don't want it to try to lock all the stuff we're mmapping into RAM. We just want to lock the heap into RAM. So this does imply that you should set your maximum heap size to the same as your minimum heap size. This is what Cassandra does by default. Some of the other stuff that we use JNA for, POSIX advise, which lets us tell it that, hey, I'm writing out all this data in an SSTable, but I'm not actually necessarily going to need that right away. So don't blow away whatever you have in your cache now for this data that I'm writing out at this instant. If I need it again later, I will ask, but I probably won't. Similarly, when we're going through and compacting, this is a little more sophisticated. These old SSTables that I'm going to throw away, some of those rows in there are hot in the cache. So what I want to do is I want to ask it, hey, what segments of this SSTable that I'm compacting are actually part of your page cache right now? And then as I go through and merge those, I will ask you to preheat those in the new SSTable that I'm writing out as well. Let's see, that's mncore and fncore. What do we use fcontrol for? I actually don't remember, but it's in the source somewhere. Digressing a little bit about Java native access, this is what that looks like. Basically, you just declare what functions you need to call at the bottom here, private static native int mlock all, and then you just give it, you just need to initialize the library that you're using with native.register. So it's actually pretty cool, and it wraps the C-level error no API into this last error exception, which mostly works. It works in that it will tell you if an error happened, but you don't actually know what the error means unless you have access to the C headers on that particular system. So it's better than nothing, but sometimes if we go and we call mlock all and it doesn't work, all we can log as far as Cassandra's concerned is we got error 1 back. So good luck grepping for that, right? Occasionally, usually everything works fine, and when it doesn't, it's usually the user misconfigured something and he didn't have permission as user Joe to lock 8 gigabytes of stuff in memory. So the easy workaround is if you start seeing native error numbers in your Cassandra log, is try running as root and seeing if that makes it go away. And if it does, then you can adjust appropriately the permissions you've granted your Cassandra user. There's a similar library out there called the Java Foreign Function Interface that's used by JRuby and the JRuby guys swear to me that it's faster and better, but it's also entirely undocumented. So should you feel like performing a good deed for the world of open source, go document JFFI and drop me an email. But in the meantime, JNA works pretty well for us. We've actually dug into it and fixed a few bugs for them. So at this point, as far as Cassandra is concerned, it's pretty solid. So we don't feel any particular urgency to move off of it. So just to kind of summarize this last section, Java started off with this, 100% pure Java, write once, run anywhere, and that's great. But in 2012, people are using Java to run servers, not to make Duke dance in your web browser. I really like the Python approach, which is that we'll give you portability where that makes sense, but where it doesn't, or where it's more effort than it's worth, then hey, we'll still expose that functionality in the standard library and trust you as a responsible adult to use that power wisely. So the example here is there's the GNU readline library, which we actually also use in the Cassandra shell, which happens to be written in Python. That provides command line history and things like Emacs key bindings as you're editing your command lines. Should you be into Emacs? And so you get that on basically Unix style operating systems. On Windows you don't. So on Windows the Cassandra shell does not really give you it doesn't give you readline style editing. So you can do things like try import readline, catch an import error, fall back to whatever you were going to do on a system that doesn't support that. So that's a place where I think Python made the right decision. Incidentally, earlier this year, lest you think that I'm on the wrong side of history here, at PyCon earlier this year, I gave a talk on what Python can learn from Java. So I'm trying to preach to both worlds a little bit. The other thing that's obsolete is trying to protect people from themselves. So a great example of this is what we've had to do with mmap. I get that munmap is dangerous and it can cause seg faults. I know because I've made JVM seg fault by using it. But when you need it, you really need it. And trying to protect me from that didn't stop me from seg faulting things. It just made me have to go to reflection and non-portable code to get that power. Finally, one of the other pain points, much more minor than these other ones, but worth mentioning, is that a lot of really useful stuff in the JVM is hidden under this banner of unsafe, and dragons be here and so forth. And this is not portable, even though pretty much any high performance Java library uses unsafe, even if they don't admit it. Sunmisk unsafe actually exists in the IBM JDK and everything. So at least the important parts are as portable as you need them to be in practice. So one of the big places we use it in Cassandra is a library called non-blocking hash map, which gives you significantly better performance with high thread counts than concurrent hash map does. This is also what we use for doing malloc, by the way. You can ask Sunmisk unsafe to allocate native memory for you, which of course the JDK needs because you can do that with direct buffers, but we also use that to do our freeable memory stuff, and malloc can free that. So this was fun because even this is a real publicly supported option to the JDK. This was the place I learned about it on Twitter. This is as of Monday. This was not documented on the list of JDK startup options. So Now that's a problem when knowledge has to get disseminated in ad hoc fashion like this. And if you're curious about what this does, by the way, Cassandra does enable it by default now. If you're curious about what it does, there's a blog post by the guy who wrote it, and you can find that. Super frustrating when you have to crawl through mailing lists and blog posts to try to figure out what options you need to get the behavior you want. So I've harshed a little bit on Java here today. So I just wanted to end on a positive note. From Cassandra 06 a couple years ago to 1.0, we increased write performance by 30% and read performance by 300%, which isn't too shabby. Overall, I would still build Cassandra on the JVM if I had to do it over again. It gives us the right combination of performance and rapid development. In particular, being garbage collected almost all the time is the right thing to do. It is nice to be able to escape into native memory for small pieces of the application like we've done. And I wouldn't be sorry if that were given more first-class treatment in the JDK. But as it is, garbage collection is the right default. So with that, I'll be happy to take questions.
Before we're coming through, we're actually working with portability to provide with that on-site taken out of some of this. I think just get it out from the open. JDK8, for example, uses it itself for switching libraries, so it's like what much.
Thank you, sir. You are doing God's work.
So I was wondering why you use JNA instead of JNI, because JNI is so much faster.
So that's the question is, why do you use JNA instead of JNI? Because JNI is so much faster. In our experience, well, okay, so basically, JNA gets us close enough, and I haven't looked at their benchmarks, but the JNA people claim that they get within 10% or so of JNI, which is pretty good, and that's worth not having to deal with distributing binaries for different systems. All I have to do is, all of Cassandra is Java, and then I just have to bind to libc and maybe create different interfaces for different libcs. And I don't ever have to deal with compilers and make files and so forth. So small performance hit, but seems like it's worth it so far.
What's the overhead of dual memory and training with the tool?
The question is, what's the overhead of using the Java agent for memory management? It's substantial. You can't do it in real time. So what we do is we take a sampling approach. So basically, every time that I've done every doubling of operations that I do, I will resample the memtable and see if the ratio of your data size to overhead has changed, and then I adjust my assumptions accordingly. So what we do is we record the ratio, and then for the in-between samplings, I just track on how much user data has come in and multiply that by the ratio to get an approximation of how much actual heap space it's taking up. Because it's far too slow to actually recalculate that every time we update it.
That's why it keeps up, taking it keeps up.
So we could... Yeah, I mean, we take heap dumps frequently to analyze the characteristics. But the thing is, we want this to adjust itself automatically to different user-level workloads.
So it's not just the tool that it's not just measuring the overhead, but also some built-in functionality to adjust something.
Right. What it's adjusting is how fast do I have to flush those out of memory. So that's what it's doing. Yeah, I'll be glad to take Cassandra-specific questions offline, but I want to keep this for what we're doing at the kind of the more lower level.
You mentioned before you were doing records counting, and you were going to look at some kind of metadata, is that right? Is your node job, you don't worry about any circular referencing there at all?
So the question is, are we worried about circular references with our reference counting? And no, and we basically have to hand audit it to make sure that we don't need to worry about that. But in this case, the native memory is just a blob, so it can't reference any other objects on the heap, so it's not a problem.
So didn't you think of using some caches like EF cache and
The question is, did we look at EH cache or anything like that? So our caching is built on a library called concurrent linked hash map, which is basically it's basically part of the Guava map builder, but it's been pulled out and made a standalone library. It exposes a few tuning knobs that aren't exposed in the Guava version, and it's substantially faster than EH cache. So we don't need a lot of the fancy bells and whistles from EH cache. We just need a raw, cache that can provide least recently used eviction, and we get that with concurrent linked hash map.
Have you ever thought about using some Oracle private API to map regions more than 2 gigabytes?
So the question is, did we consider using a private API to map regions larger than 2 gigabytes? We could definitely do that using JNA and going straight to the OS and say, mmap this large region for me, right? The problem is that byte buffer only lets me address 32-bit offsets. So
You said that it seems to be using a lock, actually. I once looked into this code that was super expensive. It seems to be 64 now.
yeah, but if you start to use reflection to get to that, then the overhead of reflection is larger than what you want on a cache path.
No, but you could use on-heap API to access memory mapped by private API.
Yeah, maybe if you could outline what you're thinking of, come get my card afterwards and shoot me an email. Then that would be interesting. Yeah, we don't require JDK7. Yeah. But JDK6 is the end of life, I think, is this month or November, so it's coming up. Oh, they pushed it out again? Yeah. So yeah, eventually we will require Java 7, but yeah. There was another hand, I think, but I guess he decided against it. All right. Basically, the 2 gigabyte column value limit is from byte buffers again. That maybe we could go get around that, but having all of that as one single blob probably isn't a great idea to begin with, and B, it's awfully convenient to work with the JDK and use byte buffers that I can pass to channels and so forth. All right, thanks, guys.